So today in AC electrical circuits, we're working on lab number 4, inductive reactance. Inductive reactance will be examined in this exercise. In particular, its relationship to inductance and frequency will be investigated, including a plot of inductive reactance versus frequency. And you can see I've given you a couple of reference sections in Sherman's Outline Basic Electricity 2nd edition. We've already investigated Chapter 12, Principles of Alternating Current, so I just want to give you a glimpse at Chapter 13, Inductance and Inductive Reactance. So Chapter 13 in Sherman's Outline covers induction, characteristics of coils, and inductive reactance, complete with the formula for XL equals 2 pi FL. And it gives you some pretty nice waveforms for inductance, and you can see that IL lags VL by 90 degrees, gives you the phasor diagrams, and gives you a whole bunch of problems to work on, and they're all solved in the book for you. So under theory overview, we're talking about the current voltage characteristics of an inductor being unlike that of a typical resistor. So while resistors show a constant resistance value over a wide range of frequencies, the equivalent ohmic value for an inductor, known as inductive reactance, is directly proportional to frequency. So the inductive reactance may be computed via the formula XL, which is inductive reactance, is equal to J, that's plus J, 2 pi FL. And F is the frequency. So as you change the frequency, you can see you're going to change the value of XL. And continuing on, under theory overview, it says the magnitude of inductive reactance may be determined experimentally by feeding an inductor a known current, measuring the resulting voltage, and dividing the two following Ohm's law. Now it says an AC current source may be approximated by placing a large resistance in series with the AC voltage, the resistance being considerably larger than the maximum reactance expected. The equipment we're going to be using an AC function generator, and we're going to be using the circuit test SWF 7000. Your oscilloscope is going to be the Tektronix. It's either the TDS 210 or the TDS 1002. And our DMM, as always, is the Mastech MSM 9803. And we're not going to bother with the serial numbers. And you can see our schematic is going to be fairly simple today. We're just going to have the AC function generator going through a resistor and an inductor, so it's a basic series circuit. So under our procedure, we're going to create a current source just using a standard function generator, so don't worry too much about it. Using the circuit of figure 4.1 with Vin of 10 volts peak to peak and R of 10K, and assume that the reactance in the inductor is much smaller than 10K and can be ignored. So we're basically ignoring our inductor in the circuit, and we're going to determine the circulating current using the component values and record in table 4.1. So we're just going to have a 10 volt peak to peak going through a 10K ohm resistor. So using Ohm's law, V equals IR, I equals V over R, we're going to take our 10 volt peak to peak and divide it by our 10K ohm resistor, and we're going to end up with 1 milliamp, and note that it is peak to peak. And finishing off step 1 under procedure, we're going to be measuring our resistor and our 2 inductors that we're going to be using today, and we'll record those results too. So I just wanted to show you our 2 inductors for today. One's labeled 102 and one is labeled 103. So the 102 is going to be 1 millihenry and 103 will be the 10 millihenries. So using my ohm meter and checking my 10K ohm resistor, we can see it's 9.96K ohms. So checking my 1 millihenry inductor, you can see it's approximately 1.9 ohms. So checking my 10 millihenry inductor, you can see its resistance is a lot higher at 22 ohms. So I've recorded the model numbers for my equipment and X'd out the serial number because they were too hard to find. I've written down the resistor values. So my actual value for the 10K is 9.96. The resistance of my 1 millihenry is 1.9 ohms, and the resistance of my 10 millihenry is 22 ohms. A lot of times students will tell me that they can't read the number on the side of the inductor, but if you take its resistor reading, you can find out which one's the lower inductance because it's going to have a smaller coil of wire and thus less resistance. So a larger inductor will have a larger coil of wire, hence more resistance. So in table 4.1, I've made a note of my R coil of the 10 millihenry is 22 ohms, and it was labeled 103, and the R coil of the 1 millihenry was 1.9 ohms, and it was labeled 102. So under procedure, step number 2, we're going to be measuring reactance. So we're going to build the circuit of figure 4.1 using R of 10K and L of 10 millihenries. We're going to place one probe across the generator and another across the inductor. We're to set the generator to a 1 kilohertz sine wave, so that's 1000 hertz. And we need to set it up for 10 volts peak to peak. So setting up for 10 volts peak to peak will have to be done on the oscilloscope. And we're going to make sure that the bandwidth limit of the oscilloscope is engaged for both channels to reduce signal noise and to make for more accurate readings. So I've set up my circuit, and you can see that I have used the 3 binding posts that I've used in previous labs. I have the main input from the function generator going through the red wire going to one side of my 10k ohm resistor. The other side of my 10k ohm resistor goes to my inductor. The output of the inductor goes to the black wire that goes back to the common of the function generator. At the midpoint, I have a yellow wire at the junction where the inductor meets the resistor. I've taken my inductor out so you can see that the yellow wire does indeed connect with one side of the resistor. It's very important when you're putting the inductor in the circuit that you don't spread the leads too far apart, or they will break off the inductor. The inductor itself is made of very, very fine wire, and these long legs are soldered to that fine wire, and if you pull on them too hard, they'll break off the wire. So 103 is my 10 millihenry inductor. So channel 1 of my oscilloscope will go to the white terminal. Channel 2 of the oscilloscope will go to the yellow terminal. And all the black commons go together in my red terminal. In the previous lab, I showed you how to set up the function generator. Remember, all these knobs must be pressed in, and this last one here for the sweep has to be fully counterclockwise. We're going to be using the sine wave, and we want the multiplier to be 1K. And we want to set the main dial so our display says 1 and the K light is lit in the display. We're going to be plugging our BNC to banana into the output terminal, and after doing a factory reset on your oscilloscope, set up your waveforms. So we can see I have channel 1 menu button pressed in, my coupling's on AC, my bandwidth limit is on at 20 megahertz. Volts per division is coarse, probe is ×1, and the invert is off. You'll notice this is my main sine wave. I've adjusted the amplitude per division to cover 1, 2.5 divisions. My oscilloscope is set to 2 volts per division. So 2.5 times 2 is equal to 5. So it's 5 volts peak. and our lab asked us to set up the sine wave to be 10 volts peak to peak. So I have 5 volts at one peak, minus 5 at the other. That's 10 volts peak to peak. Notice I've put channel 2 on 2 volts. So if I press the channel 2 menu button, you can see it's on AC, bandwidth limit is on, volts per division is coarse, probe times 1, and the invert is off. And my channel 2 is at 2 volts per division. And you can see the waveform barely moves. If I adjust my volts per division, I'm now at 1 volt per division, 500 millivolts per division, and you can now start to see a waveform developing. If I adjust it to 200 millivolts, 100 millivolts, now you can see I'm getting a fairly thick waveform. It's at 100 millivolts. That's a very, very small signal, and we're getting a lot of noise being picked up on all the wires that we've hooked our circuit up with. To clean up our waveform, we can press the Acquire button, and the Acquire menu comes up. Right now we have it on Sample. We can select Average, and I've selected 64 averages, and that gives us a better looking sine wave on our output. It actually takes the average of all that noise that we were getting in and cleans up the waveform for us. So under procedure, step number 3, we're going to calculate the theoretical value of XL using the measured inductor value and record this in table 4.2. So in table 4.2, we have a frequency of 1 kilohertz, and we want to calculate XL. Now XL is equal to 2 pi FL, and L is 10 millihenries, F is 1K. So the equation becomes 2 times pi times 1K times 10 millihenries. The calculation is 2 times pi times 1 times 10 to the exponent 3 times 10 to the exponent minus 3. And that equals 62.83 ohms. So in your table, write down 62.83 ohms. Remember, XL is resistance and it's measured in ohms. So under procedure, step number 4, we're going to record the peak-to-peak inductor voltage and record this in table 4.2. So on my oscilloscope, I've used the measure button, and on channel 1 I have it showing frequency, and on channel 1 I have the period, and on channel 1 I have the peak-to-peak voltage, which is the 10 volts that we were supposed to set it up for. And on channel 2 I have the peak-to-peak voltage as 68 millivolts. This is the voltage drop across my inductor. So I'm going to record the peak-to-peak inductor voltage in table 4.2. Under procedure, step number 5, we're using the source current from table 4.1 and the measured inductor voltage to determine the experimental reactance and record it in table 4.2. We're also going to compute and record the deviation. I just want to remind everybody that to calculate deviation, we're going to use the percent error formula, and this was shown below in lab number 1, where percent error equals the absolute value of the theoretical value minus the experimental value divided by the theoretical value times 100%. So for XL experimental, V equals IR, basic Ohm's law. R is equal to V over I. So V equals the 68 millivolts, and I equals 1 milliamp from table 4.1. The answer being 68 ohms. So the 68 ohms experimental compares favorably to the 62.83 ohms calculated in theory. Under procedure, step number 6, we're going to repeat steps 3 through 5 for the remaining frequencies of table 4.2. So for a frequency of 2 kilohertz, you can see my channel 2 peak to peak is now 128 millivolts. To get to 3 kilohertz on your function generator, you're going to need to go from the times 1K to the times 10K range button. So at 3 kilohertz, the voltage across the inductor is 196 millivolts. At 4 kilohertz, the voltage across my inductor is 256 millivolts. At 5 kilohertz, I'm starting to get my screen cluttered up and I can't see what's going on. So I'm going to change my seconds per division. So I was at 250 microseconds. So I'm going to change it to 50 microseconds. So my frequency is 5 kilohertz or close to it. And the voltage across my inductor is 312 millivolts. At 6 kilohertz, the voltage drop across my inductor is 372 millivolts. Now notice we jumped 2 kilohertz in frequency. We're now at 8 kilohertz, and the voltage drop across my inductor is 500 millivolts. At 10 kilohertz, the voltage drop across my inductor is 632 millivolts. So you can see on table 4.2, I've put down the voltage across my inductor for all the different frequencies. I'm going to come back later and do the calculation for XL theory, XL experimental, and percent deviation. Under procedure, step number 7, we're going to replace the 10 millihenry inductor with the 1 millihenry unit and repeat steps 2 through 6, recording the results in table 4.3. So I've replaced the 10 millihenry inductor, the 103, with the 1 millihenry inductor labeled 102. So on table 4.2, the frequency range was 1, 2, 3, 4, 5, 6, 8, and 10 kilohertz. On table 4.3, the frequency now starts at 10 kilohertz, and we work our way up to 100 kilohertz. So having replaced my 10 millihenry inductor with the 1 millihenry inductor, I have my frequency at 10 kilohertz, and my channel 1 peak to peak is at 10 volts. My channel 2 peak to peak, which is across the inductor, looks like it's 61.6 millivolts. At 20 kilohertz, the voltage across my inductor is 124 millivolts. Please make sure you keep channel 1 at 10 volts peak to peak, and you'll need to adjust your seconds per division as you increase your frequency. To get 30 kilohertz, you're going to have to change the range setting on your function generator to times 100K. So at 30 kilohertz, the voltage on my inductor is 186 millivolts. At 40 kilohertz, the voltage on my inductor is 240 millivolts. At 50 kilohertz, the voltage on my inductor is 316 millivolts. At 60 kilohertz, the voltage on my inductor is 382 millivolts. At 80 kilohertz, now we've jumped by a number of 20 kilohertz. So at 80 kilohertz, the voltage across my inductor is 508 millivolts. And we've jumped another 20 kilohertz to 100 kilohertz, and the voltage drop across my inductor is now 648 millivolts. So you'll notice on table 4.2 and table 4.3, the voltage peak to peak dropped across the inductor seems to be about the same for both charts. So for the 10 millihenry inductor at 1 kilohertz, we're dropping 68 millivolts across it. For the 1 millihenry inductor at 10 kilohertz, we're dropping 61.6 millivolts across it. Under procedure, step number 8, we're going to be using the data of tables 4.2 and 4.3 to create plots of inductive reactance versus frequency. So in order to plot inductive reactance, we need to calculate it. So that's the XL EXP column in both tables. To get those columns, we'll remember that XL is measured in ohms, and basic Ohm's law is V equals IR, so R equals V divided by I. So we're going to take the voltage readings for the inductor at the different frequencies, and we're going to divide it by our I source. So once you've got all your calculations done for XL, you can move on to the plot. So to plot inductive reactance versus frequency, we're going to turn our paper sideways and put it in the landscape mode. So you can see table 4.2 goes 1 kilohertz, 2 kilohertz, up to 10 kilohertz. And I want to graph that on the same chart as table 4.3. So you can see the frequency on table 4.3 goes 10, 20, 30, all the way up to 100 kilohertz. And along the horizontal axes, I'm going to plot frequency. It's in kilohertz. And I have to go from 10 kilohertz to 100 kilohertz. So I'm going to do it in 5 kilohertz increments. And that'll take me all the way down to 100 kilohertz. So XL on table 4.2 goes from 68 ohms up to 632 ohms. And XL on table 4.3 goes from 62 ohms all the way up to 648 ohms. Now the vertical axis is XL, or the inductive reactance. Remember, this is measured in ohms. So I have to go all the way up to somewhere around 650 ohms. So if I do it in 50 ohm increments, that will get me up to 650 ohms. Now plotting the line for L equals 10 millihenries is going to be difficult because there isn't subdivisions between the major grid divisions. So 1 kilohertz is going to be about there, 2 kilohertz about there, 3 kilohertz about there, 4 kilohertz somewhere around there, 5 kilohertz will at least be on a line. Try to do the best that you can, and remember that when you're joining these dots they will be a straight line, so try and get the best fit for those dots that you've plotted on here. Plotting the points for L equals 1 millihenry will be a lot easier for you because those dots will go on exact lines. And once again, this is going to be a linear graph, so try and draw your line through the best fit of all the points. So this is what your finished graph should look like. You can see the higher the inductance, the more vertical the line. The lower the inductance, the more horizontal the line. So this graph shows you what L equals 10 millihenry looks like versus L equals 1 millihenry. As with most labs, there are questions to be answered once you've completed your graph. So looking at question 1, what is the relationship between inductive reactance and frequency? Well, I think it's linear because it was a straight line. Question 2, what is the relationship between inductive reactance and inductance? Well, we used two different inductors, and I think the slope of the line has something to do with this answer. If the 10 millihenry trial had been repeated with frequencies 10 times higher than those in table 4.2, what effect would that have on the experiment? Well, thinking about it, the chart would have been easier because the frequencies would have been the same for both charts. However, the amount of resistance would change, so we'd need a longer horizontal axis. Do the coil resistances have any effect on the plots? For the 10 millihenry inductor, the coil resistance was 22 ohms. So XL is 68 ohms, but our series resistor in the circuit was 10 k ohms. And you have to remember that the current through an inductor rises at 90 degrees. So you have to remember the XL formula is at J, which is at 90 degrees. So the resistance of the coil has to be compared to the resistor that we used in series, which was 10 k ohms. XL of the inductor is at an angle of 90 degrees. So the resistance of the coil makes no difference to the inductor and is insignificant compared to the 10 k ohm resistor we used in our circuit. When you've completed your lab, show it to your instructor so that they can initial it to indicate that it is complete.